Our next speaker is Dr. NormanChang. Norman has been around the Bay Area for a while. Probably shouldn't need any introduction. Myself, I have in the mid 90s, I think, when I was finishing up my PhD, looking for my first job. Norman was at the XP lab. So talking to Norman and his team was one of my first interviews ever. So that's how I know Norman. I think a lot of people on the call today probably know Norman around different ways. But nonetheless, here is the introduction. Norman co-founded Apache Design Solutions in February 2001 and currently serves as ANSYS Fellow and Chief Technologist of Electronics, Semiconductor, and Optics BU in ANSYS. He's also currently leading AI and machine learning and the security initiative at ANSYS. Before Apache, he led a research group on the research of power signal thermal integrity of chipsets at the XP lab. Dr. Chen received his PhD in electrical engineering and computer science from UC Berkeley. So we have a Stanford and Berkeley representation today. He holds 23 patents and has co-authored over 60 technical papers and a very popular book on interconnect analysis and synthesis. He's currently in the committee of EDPS, ESBA EDA, SI2 machine learning special interest group, and he's also a IEEE fellow. Welcome, Norman.
Thank you, Wekai. And thanks for the invitation. It's always exciting to talk about the future and what's upcoming. So I'm going to focus on reliability and security for advanced 3D IC system. And the previous Jimmy and the CT gave a very good background and also the focus on the advanced 3D IC and optimization that we need to perform. In terms of 3D IC, there are several applications that we can see. For the 5G, 6G design, there's analog and mixed signal design combined with digital processing. For example, that people are looking at gallium nitride combined with a digital process. So we'll see that there's a high frequency demand for that kind of design. You can see that a lot coming from ISCC this week. In the second area, for the HPC and cloud application, a lot of GPU and CPU design, the power demanding is continuing to increase. We can see there are 300 watts, 500 watts, or even 1,000 watts and more. Therefore, the power density continue to increase. Given the 10 micron by 10 micron, we can see that it's go beyond 5 milliwatts or can reach 10 milliwatts in certain design or the testing scenario. For automotive application, reliability is particularly important because automotive electronics have to work from -55 all the way to 155 in certain cases under the harness. So the reliability going down combined with the 3 nanometer, 2 nanometer, the on-chip wear-out mechanism and the chip packaging system, the agent mechanism becomes very important and very serious problem. Security is always in the picture. And from the DoD point of view, security has a combination of the rule of trust in terms of the hardware design. So we will look at some of the opportunities for the side channel leakage and the fault injection perspectives. There are three aspects for packaging mechanical stresses. The first category is thermomechanical induced stress. For this kind of stress type, there are dielectric cracking, interfacial cracks, solder joint fatigue, and copper trace cracking, and also including the package delamination modes. And you can easily see that from the measurement lab. The second category is becoming more popular. It's a high-growth mechanical stress. That's because we are using the fluid in the thermal mitigation in the data center. So there are moisture around the package design, and that can cause the vapor pressure induced popcorn popcorn cracking, that kind of failures. For the relevant design failure is electrothermomechanical stress. This is due to the electrical current flowing through the TSV, C4 bump, micro bump, solder joint, and there are a lot of currents. And when the current, a lot of current flowing through the wire, that will have a geoheating induced temperature increase. And also when the temperature increase, the leakage power also increase. And that in terms, inversely, that will increase the current going through the wires. Eventually, that will cause the void and the heel lock in the electromigration phenomena. And this problem, electromigration has a new challenge in terms of the TSV, RDL layer, the fan-out WLP design, because the shape of the design for the metal conductors is not rectangular. It can be 45 degrees. It can be a big piece of metal. So in terms of the calculation of the electromigration and the direction of the current is not certain, and that becomes a new problem when we're going down to 3 nanometer and 2 nanometer designs. So let's look at a chip packaging system reliability perspective. And in the manufacturing defects area, and that comes from the process, but in the ESD, EOS, and SEE for the extrinsic random failures, that the non-contact system level ESD becomes more and more important for the complicated system that we are building. For the electromagnetic interference and the EMS solution is also needed. And there's a new failure mechanism related to the silent data, as mentioned by Jimmy, is maybe caused by soft error, maybe caused by single event burnout or single event effect. And that may be related to the radiation coming from the alpha particle for the total ionizing dose. So these are the new problems that even that you have a data center, but you cannot prevent those problems that can cause a serious silent data corruption. The other areas of the reliability combined with the 3 nanometer, 2 nanometer is that for the gate oxide dielectric breakdown is becoming more serious, and that including the IMB dielectric. And that's because combined with the 2 nanometer, 3 nanometer design, and that we have to look at the surrounding temperature for the location of the transistor or for the cell. So with the different transistors, even on the same cell, they can see different wear-out effects. And for the different arcs of the timing arcs for the same cell, they may also see different wear-out effects. Now we had a paper at DSC 2018 talk about the clock gating effects that can cause a symmetric agent in different timing paths. And that essentially describe the problem is becoming more serious, that including the MBTI as well. For the 3D IC problem, let's focus on the thermal and the stress. Here on the left, according to the VP Doc Yu, mentioned that temperature should be the fourth dimension when we design the chip, including the consideration of the power, performance, and area. So for the left part is a CoWoS-based design, and people are putting in 5 chips, 10 chips, or even 20, 30 chips on top of the CoWoS. In the center is a new design style for SOIC, System on Integrated Circuit. We can see that example coming from AMD, that they have a V cache on top of the active die using the SOIC. And for the stacking of the 5 dies in the vertically stacked dies in using the SOIC, the thermal mitigation in the center of the dies will be more difficult compared to the other side of the die closer to the heat sink. And there are other kinds of styles of the design, including the chip on wafer, or all the way to Cerebrus design, using the whole wafer as a design, including the trillion number of trillion transistors, that the vertical voltage regulator for the power delivery, and also the thermal mitigation has to go vertically in on every location of the service. So Intel recognized the same problem. On the left is a Ponte vector design for the latest, the next GPU platform. We can see that for that design, they have to use the best thermal interface material and interface to the integrated heat spreader. And due to the height of a different location of the 3D IC design, they have to design the structure to support the structure robustness. So they recognize that the cross-die thermal coupling will be important. And when you perform the co-optimization for the thermal dissipation, we need to consider both chip and package design in 3D IC as a whole for the best thermal mitigation mechanism. And this can be illustrated by this graph. On the top die and the bottom die, we can see that each die will have a different thermal hotspots. However, if the thermal hotspot on the top die and the bottom die line up together, that will create a global hotspot. For example, on the right, that instead of the coming from individual die, you may see 35 to 44 degrees thermal hotspot. But when the top die thermal hotspot and the bottom die thermal hotspot line up together, now you can see the global hotspot becomes 58 degrees to 71 degrees. And this demonstrates that this could be a serious problem when you stack up the dies vertically together. Therefore, there's a solution needed in order to solve designers' 3D IC, large 3D IC design. That may involve 10 dies, 20 dies, 30 dies. You need a different solution. Like you cannot do a uniform partitioning, uniform meshing everywhere. Like we have to perform intelligent adaptive meshing. We may need to use a machine learning based technique or some other technique to speed up to adaptive meshing, so we can speed up the simulation time. This is a good example that one of the CPU, GPU designer, they have many dies on top of the CoWAS, and this is pretty popular among all the CPU, GPU design houses. Here is an example for the machine learning technique that we use subdomain partition for the chip. And then the unique characteristics of this approach is that we keep the flux conservation between the subdomain. I borrow the technique from the finite element method, and that will ensure the correctness crossing the subdomain for the heat flux, so we can get a very accurate thermal distribution on the die. So on the right, you can see that compared to the MAPDR, which is ANSYS mechanical with ML solver, now we get a pretty good result, and we can save 100 times X or faster compared to the finite element method. The other problem is the thermal induced stress. Because of the different material, they have a different coefficient of thermal expansion. On the bottom left, the silicon has 2.6 ppm per degree, and the substrate or the packaging has a 14 ppm per degree, and including the PC board material. So when the temperature increase, they will see a different expansion rate, and then you will see the strain and stress will occur. And so the thermal induced stress, including the warpage and the strain and the stress, happen in the ELK, extreme low K area in the dielectrics, will be a damage to the 3D IC system. Therefore, there are two considerations that we can do from the architectural level. When we design the 3D IC, we can consider the power partitioning for the different chiplets and the 3D IC, and that also including the present route for the 3D IC. And at that time, we need to consider what's the impact to the thermal and the stress during the architectural level design for all the functional benchmark and all the scenarios of the working scenario. That's why on the bottom right, you will see the transient power profile that will induce the transient temperature at different location at different time. And this has an impact to the agent, to the EM, IR drop, and also has an impact to the testing, especially important for the 3D IC design, including the vertically stacked dies. And we can get a lot of information coming from the emulation in terms of the change in power profile for different blocks in the 3D IC. And this is a big challenge for the thermal and the stress simulation, because we are seeing that there are 300 time points or 400 time points or even more. And we need to calculate the change in temperature in terms of the millisecond resolution. And that will be a big challenge for the finite element method. So here's a summary that we get. We also contributed a slide for this slide to the HIR roadmap yesterday. This is for the 2023 HIR roadmap chapter for the thermal mitigation. And we can see that in addition to the two challenges talked about on the previous slide, and there are other challenges, including the silicon photonic system, that the thermal heater design is very important for the PIC. So here we need to solve the thermal environment surrounding the PIC in the interposer. Once we get the temperature, and then we can calculate what's the waveguide and the laser property using the simulation again. And the thermal heater is very sensitive to the waveguide property for the resonance, which has a property of plus minus 1 degree. So it's very important to see how do you design the thermal heater effectively for the PIC design. For testing, that's another challenge. We are looking at a millisecond. The dynamic thermal hotspot will move from one IP to the other IP. And this will happen very quickly. So this will impact your test sequence and also the test frequency. And that will contribute directly to the increase of the temperature locally and also to the dynamic voltage drop locally. And so you need, when you run the testing on the Teledyne or the Avant test, you need to know where is your peak transition temperature occurring. The other area I want to talk about is that for the industry, is that we need to have an open and extensible AI ML platform, not only for system technology co-optimization, but also for the design space optimization, as mentioned by Jimmy. So here we try to provide the API for our tools, including ADT or the CSCAP platform. Now we have an API to provide designers to have access to the some of the internal, external information, and they can use that information and write a Python script or using the OptiSLAM for the co-optimization. Let me talk a little bit about the OptiSLAM, which is a company we acquired 4 or 5 years ago. For this powerful auto ML platform, that the whole thesis is situated on the design of experiment for the deficiency of the area for the data. So it's controlled by the coefficient of prognosis. And by looking at the input and output on the bottom left, you can do the explanation that which input is more important for the output. So after you design the range of the input, the meta model, which is a machine learning model or can be a statistical model, can be created automatically and will run through the other combination of the input space to give you the best runtime for the application. Let me give you an example for this one with a Samsung. So this is a mobile processor, and they simplify the change in temperature derivation based on the thermal material properties for the packaging and the PC board. So we are looking at the input parameters, including the HTC, the thermal conductivity, the chip heat capacity, and the density of the material. So previously, this has to be solved manually between 2 to 4 weeks. But now we can solve within 4 to 5 days because everything can be automated using the OptiSLAM. So this is one way to go. I totally agree with Jimmy that AI ML will play a big role in terms of automation, and we can see more improvement in the future. So right now I want to switch to another area for the security very quickly, and just a couple of slides. For the security, that we can see that from the Intel processor and the NXP processor and also the Apple A10, they all got cracked using the EM side channel, and the Intel one is using the internal power monitor. And the side channel means that you can use some of the power noise or the electromagnetic emission coming from the die and use that information during the encryption operation of the AES, for example, that you can get to crack the key. And this is becoming a very serious concern from the designers and the DoD. So this is exactly a multi-physics problem that we are very happy to look at a security problem, because every phenomenon can take a new kind of multi-physics simulation for analog mixed signal design, for the screaming channel, for the RTL gate-level power simulation, thermal side channel simulation, optical side channel simulation, near-field electromagnetic emission. Is also a multi-physics problem that we can get to solve the problem, and has to solve because the equation sequence easy can be 1 million. So have to solve the problem very quickly. So one ask from the security designers is that they want to see the solution earlier. So during the RTL and gate level design, if we can provide some feedback, say where is the problem that can potentially have the leakage for the side channel, so they can get to fix the problem. They don't need to wait until the tape out from the measurement lab, certification cannot pass, and then there will be delayed by 3 to 6 months. That including the EM side channel, power noise side channel, and also the chip package system side channel simulation. We have a tool called RTL and a gate level side channel that we just come out. And this when we can run 1 billion vectors for the AES encryption or other kinds of post-quantum security protocols. And then that we can identify the security sensitive assets, and we can also run the root cause analysis for the potential problems, so they can get to fix those problems. The other area is the electromagnetic side channel. Now we calculate the electromagnetic on top of the surface or on the substrate side, and that can be a 100 micron away, similar to the EM probe. And not only that, we can try to identify where is the location that we can give this information to the measurement. Say these are the potential locations that can have an EM side channel leakage. So that can save the measurement people a lot of time, or including the certification and the diagnosis people. And we won the best paper last year. So we come for a long time, including all the multi-physics phenomenon for the past 22 years, started with Apache Design Solutions. We started looking at power and reliability, thermal stress, EMI, EMS, reliability, silicon photonics, and thermal induced stress. So there are all kinds of multi-physics problems, and designers get to trust this analysis with the tools that can provide a multi-physics simulation. On the other side, if you look at the security, for the security designers, this is a brand new experience. So we started with the RTL and the gate level power side channel and the EM side channel. But the next we can look at the security protocols in the 3D IC, which has a different spin of the flavor to consider power in the EM side channel. And we will continue to look at the EMFI, which is electromagnetic fault injection, and also the laser-based fault injection, and many other phenomena from the security. But for security designers, this is a new experience. So it will take some time for them to adopt the solution. And luckily, we have several customers already think this is important and adopted the solution. So we see that this is another great opportunity for the security community for different kind of solution for security. Thanks a lot. And then maybe we can answer more questions and more discussions during the panel discussion.
All right. Thanks, Norman. That was an abrupt conclusion. I was not ready for the end of it. But thank you